Urense. And it's very good that my first remark on the pedagogics report was not recorded. And she will talk about two associahedra and fan realizations and polytopal data. Okay, thank you. Daria, you have the stage, and I will manage the camera.
Okay, hello everyone. Thank you for coming to my talk. It's my pleasure to be talking at the seminar, and I will talk about a family of polytopes to be, which are called two associahedra, which are a natural generalization of usual associahedra, one of generalizations. And most sort of the first part of my talk would be advertising those polytopes and why you should like them. And the person to whom the definition belongs is named Bottman. And then I will proceed to talk about our ongoing project with Nate and with Spencer Beckman. Okay, so let me begin from a little reminder on usual associahedron. So usual associahedra are, as it follows from their names, the polytopes which you need to be dealing with associativity. So if you have an algebra and you have a couple of elements in your algebra, then you have a binary operation that multiplies them. Then if you have three elements, you can either multiply them in this order, or you can multiply them in this order. And if this is so if this is happening in an associative algebra, then these two things are supposed to coincide. So associahedra are polytopes that deal with a situation where this thing and this thing are different from each other, but not very different, homotopy. So the one-dimensional associahedron is the interval, and what it tells us is that there must exist a trinary operation that the differential of which is equal to the associator of the binary operation. So so this is the reason why people are interested in associahedra now. What are they as topological spaces? So as a topological space, the associahedron IM is the moduli space of endpoints on Li, modulo translations and dilations. And then compactifies. So let me explain how precisely we compactify. Let me do that in a two-dimensional example. So two-dimensional example corresponds to 4 points. Why 4? Well, because the dimension of this part is the number of points. Then you lose one item of dimension on translations and one item on dilations. So you are two-dimensional for n equal to 4. Then let us draw the usual pentagon. Spoiler, but everybody knows that A4 is a pentagon. So So now if we have 4 points, let's call this distance A, let's call this distance B, and using the dilations, let's make sure that the last item is 1. Then to an element of this moduli space like this, we can associate a formula of numbers as follows. B, A over plus 1, A plus B, A over. So this gives an embedding of this thing into our form. And well, let me actually say that gives you the embedding of the interval from 0 to infinity closed in the 4th power. And then you just take the closure of the image of this thing within that space. Now can I use that word?
Yes, I just have to. Go ahead.
So I said that we use Associahedra to discuss infinity algebras, but let me actually say that the algebraic objects controlled by Associahedra are A infinity categories, not algebras.
One second. Does everyone see this mirrored?
No, it's
No.
like, what do you mean? It looks
So you
normal.
see this in the right direction. You can see it from left. Yeah. Sure. Okay. Why do I? Okay, I don't know why I see it this way, but maybe it's just because I'm filming. Okay, fine, good. Continue.
Okay.
Because for me, for some reason, it's mirrored.
So then for combination of points, you can say that you put an object of an A infinity category into every stretch of line. So X here, Y here, you know, W here, and for every point, you have a morphism, F here, G here, H here, and then a stratum in the Associahedra, Associahedron tells you how exactly you compose those morphisms, so what operations you apply to them. And strata in the compactification of such a moduli space is given by bracketing of points. So this was the reminder on what Associahedra do algebraically. Now, if they are defined like that, they are stratified topological spaces. But a pentagon looks like a polytope. So the question is, are they polytopes? The answer is yes, they are. And there exist multiple realizations of usual Associahedra, and the realization that I like most of all is due to Loday. So let me remind this realization because that will be the one that we will be mimicking for 2 Associahedra. Oh, thank you. I didn't notice that. So, well, there are 2 ways of realizing polytopes. You can either give a polytope at the convex hull of its vertices, or you can give a polytope by a system of inequalities. So I will be giving you the inequalities that define the Associahedron. Namely, suppose you have a facet. So a facet is a bracketing that has only one bracket. For example, let's say that the bracket has the first 3 points. So first of all, you need to have a normal vector for that facet. We will be having a normal vector in the vector space, which is one dimension up. So we will be embedding a two-dimensional object into R3, but it will land into a hyperplane. So to this facet, the normal vector that you associate is 1, 1, 0. The rule is if the 2 points sit inside the bracket, then you put 1. If 2 points do not sit inside the bracket, then we put 0. So in some other way, you can say that if this bracket corresponds to a collision of these 3 points, then after the collision has happened, you go from the situation where the points were at levels 0, 1, 2, and 3 to the situation where 3 points sit at level 0 and 1 point sits at level 1. And then you can say that the coordinate xi in the normal vector corresponding to this facet is equal to the change of distance between the I minus first point and I point. Indeed, let's make sure that that's what I've written here. S1, this is the change of distance between the first point and the 0th point. Here, this distance is 1. Here, this distance is 0. So it's 0. X2 is the change of distance between these two guys. Here, they are separated by 1. Here, they sit together, so it's 1 again. And X3 is the change of distance between this and this point. Here, they are separated by 1. And here they are still separated by 1, so it's 1 minus 1. We did get 1, 1, 0. So this is the normal vector corresponding to this facet of associahedron. So I'm half done with realization. Then I should say what is the value of the support function on this vector. And the value of the support function on this normal vector is given by counting the number of pairs of points that collide in this bracket. Let me write it down. So support function, number of pairs of points in the bracket. So in this example, the number of pairs of points in the bracket that has 3 points is equal to 3. This pair, this pair, and this pair. So the corresponding inequality defining this facet of the associahedron says that x1 plus x2 has to be greater or equal to 2. And then you do that, you write such an inequality for every facet. And additionally, you have the equation of the hyperplane. Which just says that the sum of all the coordinates is equal to, well, still the number of pairs of points, but of all the points, so it's so this is Loday's realization of associahedra. It also has a nice description of vertices, which I will not give right now because sort of the facet description is simpler. And this will be the one that we will be generalizing for two associahedra. What is remarkable about associahedra realized this way? Well, they are generalized from mutahedra in the sense of Postnikov, meaning that their normal fan is a coarsening of the braid arrangement. Okay, so I guess this was everything that I wanted to say about the usual associahedra. And now let me move to the objects to which my talk is dedicated, namely, let me begin with the So, well, usual associahedra were a compactified moduli of n points in a line. Two associahedron is given, so they are a bifamily, meaning that an index of a two associahedron will be not one number, but a bunch of non-negative numbers, and 1 to nk, each of them 0 or larger. And this thing will be, again, compactified moduli space of arrangements where you have k lines. And you have ni points sitting on every line. And as previously, modular translations and modular dimensions. Before I explain what exactly are the strata of these compactifications, let us do the simple dimension count. So, what is the dimension of W and 1 to k? Well, what do you have to fix? There are k positions for lines. That gives you dimension. Then there are n1 positions for points on this line. That gives you sum of all n1. And then translations here, they happen already in the two-dimensional space because this lives in R2, not in R1. So you lose 2 items of dimension on translations and still 1 for direction, because directions happen simultaneously in all the directions. So this is the dimension count. So let's find then the one-dimensional guys and see how they look. So let's look at W11. So, and let's use the formula that I've written over there. So we have dimension W11 to be 1 plus 1. Oh, I had to begin from, so k equal to 2 plus 1 plus 1 minus 2 minus 1. So that's equal to 1. There are not that many contractible stratified spaces of dimension 1. So it follows that W11 has to be an integral.
What happens if I take not only the global dilations, but I could take dilation in any coordinate direction? So I can stretch in horizontally and vertically.
And something else.
And something else. Okay.
Okay, so this is supposed to be an interval, but how is it an interval? So what are the strata? So you have a pair of lines with 2 points. And remember that strata should correspond to stuff somehow colliding in this picture. What are the possible collisions? Well, there are actually 2 possibilities. For any collision to happen, the lines have to collide. But then when the lines collide, there are 2 possible situations, combinatorially. Either this point is above this point. Let us draw like this. We draw the circles, and the circle that contains the left point is above the circle that contains the right point. Or when they bump together, we can have the relation vice versa, like that. So these are the 2 0-dimensional stratum, and then in the middle there is the 1-dimensional stratum. And at this moment, only having this in my this example in mind, I can already explain the algebraical problem for which you have to study those polytopes, because right now I just was like, let's study compactified moduli spaces of arrangements like that. But why do we do that? So having written this example, I proceed to the categorical motivation for associahedra. So associahedra were to define infinity categories, and 2 associahedra will be used to define a homotopy version of 2 categories. So a reminder, 2 category is something that has objects, morphisms, and morphisms between morphisms. Let me draw a picture of something that can happen in the category. So suppose I have some 3 objects. I have 2 morphisms here, and then I have a morphism here. Let's call these 2. So morphisms between morphisms are called 2 morphisms. And ordinary morphisms are called 1 morphisms. So this is the 2 morphism F. Let's call this 1 morphism the beginning of F, and this 1 morphism the end of F. And let's call these 2 morphisms here G. And let all this the beginning of G, and this the end of G. So in the strict 2 category, there is exactly one way of composing everything in this picture, so that you have a 2 morphism F composed horizontally with G that goes from the composition of SF with SG to the composition of TF with TG. But what are the elementary ways of expressing this composition? Well, here the question is, what are my elementary moves? So let's say that my elementary things that I can do in my 2 category are either vertical composition of 2 morphisms, not something that I have in this picture. or horizontal composition, but not with just anything, but with only the identity homomorphisms. So these are the only two things that I can do as my elementary moves. Then let's express this composition that I want to get here through the elementary moves. What can I do? Well, I can take the identity homomorphism of the one morphism where F begins. And I can here take the identity homomorphism of the one morphism where G finishes. So this is one of G. This is G. Then I have the no color chalk, no color chalk. Then I can over here I have an identity homomorphism that I can compose horizontally with a non-identity one. So this is an allowed elementary operation. Over here I have an identity homomorphism which I can compose horizontally with this F. So this is an operation that I'm allowed to have, and then I can compose them vertically because vertical composition is allowed to me. So this way of expressing this the total composition of this feature through elementary operations resembles the left or the right? No, the right. Yes, I'll draw that again. So let's put a dot where we have a morphism, and let's not put the dot where we have the identity. So this is a combination of elementary operations corresponding to that stratum of that feature. And now different thing to draw is we can have F here and G here. Here we have the identity of end of F. Here we have the identity of beginning of G. And this is the combination of elementary operations corresponding to the stratum like that. And oh, thanks. Yeah, so well, I just wanted to draw lines here with some color that is not white. Like that. And in a strict category, of course, this and that will have to be the same. So two associahedra are polytopes that allow for a definition of a homotopy version of two categories, where this is different from this, but there is a homotopy between this and this, corresponding to the one-dimensional stratum of W11. So before I define what are general strata in two associahedra, let me actually do one more one-dimensional example, because if we do our dimension count, then if we have W20, then the same formula says that we have what 2 plus 2 plus 0 minus 2 minus 1 equal to 1 again. So this is another two associahedron that is also equal to an interval. What are the strata in this interval? Well, this is our general picture, 2 points in one line, no points on the other line. How can a collision happen here? Well, now there are two things that can collide. There are the lines that can collide, and there are the points that can collide. So the question is, what happens first? If the points collide when they are on this line, and only then the next line bumps in, then I draw a picture like this. I sometimes draw the maximal circle, and sometimes I do not draw the maximal circle. I will be switching between that. Or it could be that first the two lines bump together, then I draw it like this. And then when the lines are already together, points collide. And the dimensional strata corresponds to the two dimension, which is when points collide at the same moment that lines collide. So we cannot see what happened first. So what is the two categorical picture that is supposed to correspond to this situation? Why do we need such a two associahedron? Well, let me draw it. So what did I say for one associahedron? I said that on every stretch of lines you put an object, and on every point you put a morphism. So for two associahedra, the rule will be as follows. For every stretch of like two-dimensional space, you put an object. For every stretch of line, you put a one morphism. And for every point, you put a two morphism. So the picture, the diagram corresponding to this arrangement of point and line is that you have three stretches of lines over here. So these are three morphisms, one morphisms that go from this object to this object. And then there is just one morphism that goes here. Let me pull down EQR S. And here I have a morphism F. And here I have a morphism G. So the question is how I can compose them into this picture into 1-2 morphism from the composition of P with S to the composition of R with S. And the answer is that there are exactly two ways that I can do this. I either can apply an elementary operation of vertical composition over here and then compose them with the identity morphism of S. Or I can, and this is what is depicted over here. I first compose them, then compose them with, there's no point here, so that's the identity. Or I can compose F horizontally with the identity of S. That's this circle. Compose G horizontally with the identity of S. That's this circle. And then compose them vertically. So this is the algebraic problem that is supposed to be solved by two associahedra. So this is why you are interested in studying the combinatorics of compactification of modular space of that thing. And now let me explain what are the strata in two associahedra. So in one associahedra, strata were given by bracketings. So strata of two associahedra are given by something that is called two bracketings. Now, two bracketings are so unpleasant to define that instead of defining them, I will explain what is a two bracketing on some large example. Let me first write an informal definition. Yeah, informal two bracketing is a depiction of an iterated collision of the arrangement of points on lines. So let's draw some rather large arrangement. Let's have 4 lines. Let's have 2 points here. Let's have 1 point here, no points here, and let's have 2 points here. So let's draw an iterated collision. First of all, let's say that these 2 points collided in the very beginning on this line before any lines collided. Then I draw a circle to say that this has happened. Now let's suppose that these 3 lines collided all simultaneously. Then I draw a bracket over here. In this picture, I will not this will actually be an extra piece of data that I will not need, but I'll later explain why you need to draw this bracket here. Then when these 3 lines collided, I already have the question, what was the order of these points? Let's say that this point collided exactly into this one. Then I draw a circle that unites them. And this one ended up being below this one. Then I draw a circle which is below the circle that has these points. Okay, so this was my second step. By the way, from this picture, I do not know whether this was happening earlier than this or this was happening later than this, but that's like the same thing that you see in a usual associahedron. If you have a bracketing like this means that these 2 points collided, these 2 points collided, and you kind of don't know what happened earlier. That is the difference between trees and trees with levels. Like if you have compactified this slightly differently, if you knew, so that you knew what was happening earlier, but then you would have got not associahedron but combinatorics. That was a side note. Let's continue drawing a two bracketing. So let's say that then now we already have these 3 lines sitting together. We have these 2 points being one fat point and this being another point. So let's say that this fat point now collided with this point. Then you draw a circle like that.
So do you also obtain a 2 permutohedron then?
I guess you could compactify slightly differently to get some other family of polytopes of 2 permutohedra. It's just that well, the algebraic motivation for them is not essentially clear.
Okay.
Well, the algebraic motivation for 2 associahedra, I prove I have explained. So then finally, this fat line can collide with this line. So we have a question, what is higher, this very fat point that already consists of 3 points, or this slightly fat point that consists of 2 points? Well, let's say that this was higher than that. Then you draw a circle like this, and you draw a circle like this. And then you may or may not draw the maximum circle to say that in the end, this was a very, very fat line and 2 very, very fat points collide on that. So this arrangement of circles that show what collided with what and what ended up being higher than what is a two bracketing. And I will not write a formal definition because then everybody would stop listening to my talk. But I think from this example, it is sort of clear what this thing is. And the strata of 2 associahedra are indexed by these two bracketings. So as as defined right now, two associahedra are stratified topological spaces that Nader Bottman introduced to be solving this and that algebraic problem. But what sort of stratified topological spaces they are? So Nate has proved in his thesis that two associahedra are CW modes. But let's actually look into some small dimensional cases to see what sort of balls they are. Let me draw the full picture of W21, and if I try to erase that, please stop me because I will need that later when I start talking about realization. So let's draw. So what do we have? We have 1 point on this line, 2 points on this line, and let's draw all possible iterated collisions of these points. It's not going to be very big. So what can happen? First of all, two lines may collide with points assembling this order, and then these 2 points may collide in the first line. That is a collision that happens in 2 steps, so this is one-dimensional. Like the number of steps is the codimension. Let me actually take another word for that, because I won't fit it into this one because too much space to write it there. That's a vertex. Then it will be that just this collision happens. I mean, and then in the end, everything collides, but I'm just not drawing this maximal circle because I'm lazy. So this is one-dimensional. Then over here, we can have that this happens, but then these 2 points collide on the double line. Then we can have that 2 lines collide and this point bump precisely into this one. And another, so this is one-dimensional. Then we can have that when the points collide, this point landed in the middle between this and that. And then these 2 points collide. Then we can have that just this landed in the middle. Then over here we have that the lines collide. This landed in the middle, and then these 2 points collide. Okay. Here we have one-dimensional situation where the lines collide and this point bumped into the lower point from that line. Another vertex of that is that when lines collide, this point got the lowest in over here. And then they collided on the double line. Then you can have a situation that the lines collide and this point was the lowest. Another vertex here is that the lines collide, but then these 2 points collided on the double line. another vertex. Okay, so then over here you have the edge that the lines collide, and at the moment that these two lines were colliding, these 2 points bumped into one another. So you sort of see it is like a very small arrangement of lines and points, but if you start listing all the possibilities, it starts getting quite a lot. So another vertex over here is that these points collided, and then the lines collided with these points getting below them. So here we have an edge where these points collided, and sort of when the lines collided, this bumped precisely into them in the very end. I'm almost there. And now here we have the observation that these points collided, and this one got on the top of them. And finally, here is this one last edge, which corresponds to the situation that the lines colliding with that point getting on the top of the left points and then colliding at the same time that the lines were colliding. Okay, so we get that W21 is end of the bar.
And what is inside?
Sorry?
Do we have something inside associahedra?
The top dimensional stratum is indexed by like the total collision. So the lines collided and all the points got into one point at the same time. But I was not drawing. So and two associahedra in general have combinatorial properties that are seemed to be enjoyed by the faithful sorts of polytopes. For example, they are to associahedra be realized as convex polytopes. And this is the question that me and my authors are currently working on. So something that is not possible. Well, we can see that two associahedra cannot be realized as generalized polyhedra. Why? Well, because here you already see an octagon, and the largest two-dimensional generalized polyhedron that you could possibly have is the hexagon. So they are a little bit too big to get into some of the single families. But we have some partial progress on answering this question, namely a theorem due to Beckman, Bottman, and myself, is that there exist complete fans. That relies to associahedra. And so then the question of them being polytopes is reduced to the question whether these fans are projective or not. And some of them are. About some of them we do not know, but we really expect that they are. But this is work in progress. And in the remaining time, by the way, how much time do I have?
I mean, in theory, you have another 15 minutes
Okay,
you can
yes.
use, but I mean, it
Great.
depends
Then
on
in the remaining 15 minutes, I will actually
50.
tell you.
You have another 50 in principle, but you can use however much you like.
Oh, yeah, okay. Well, let's see how much I will take. If it will take. So in the remaining, how much I have, I will actually tell you the construction of those complete fans.
Careful with the table on the floor now.
Okay, thanks. So, if you remember my construction of normal vectors for Loday's associahedron, then for every coordinate corresponded to the change in the distance between the points. So in the Loday's case, there was the original position that I had my points in. I said that the first is in position 0, then it's like 1, 2, 3. And I was saying that the collision corresponds to the same arrangement, but with as many points as I get left. This is the picture that I have. Now, for two associahedra, let's say that my original arrangement of points has this line in horizontal position 0, this line in horizontal position 1, and so on, like the points previously. And let's put the points, let's order the points totally from left, from down to up, and from left to right. And then let's put them in positions like 0, 1, 2, and so on. So this is the initial arrangement for W20, which I have depicted on the left. And now we will have two types of coordinates. We will have the lines coordinates, and we'll have the points coordinates. So let us draw some collision. For example, this is a facet collision corresponding to dimension 1. Then we have lines coordinates, which we'll call x's, which would be still measuring the difference between I minus first line and ith line. So in this case, the lines collided, so x1 is 1. And we will have points coordinates, which will measure the change of vertical position between the points. So in this case, y1 is 1 because they were separated by 1 and now they are together, and y2, it changes, it looks at the vertical distance between this point and this. It was 1 and it is 1 after collision, so it's 1. But so it looks like I'm still getting 0 and 1 vectors, but no, I'm not. Let's actually go to the octagon and write the normal vectors for all of its facets. So I've already done, which was it? I've done this one. So over here, I had 1 for lines, 1 for the first pair of points, 0. Over here, I have 1 for lines colliding. None of the points change their vertical position with respect to each other, so that's 1, 0, 0. Over here, I have 1 because lines are colliding, 0 because these points are still at distance 1, 1 because this point got closer to this point. But now let us look at what I have over here. So it is 0. Now these two, so it's 1 because lines are colliding. Now these points, they were at distance 1, this and this. And now they are at distance 2. So I have -1 here. And these 2 points, they were at distance 1 in this direction. And now they have swapped the direction. So I have 1, -1, 2 for the normal vector of this facet. Now over here, I have 1 because lines collided. These points, they are the same distance from each other that they used to be, 0. And now this point, it was by 1 above this point, and now it is 1, 2, 3. That's down at me. So this facet has the normal vector 1, 0, 3. And well, this has 1, 1, 2. This has, so here the lines do not collide and only these points collide. So this is 0, 1, 0, and that finishes. And then I have the, like this is a fan that lives in the space of dimension by 1 higher. So as similar to how for the associahedra, I had a separate equation for the hyperplane. On the fan language, that corresponds to a linearity space, and the linearity space is in this case spanned by a vector 1, 1, 1, like for associahedra. And a theorem that we have is that fans like that, which are not coarsening brane arrangements, so these are some more complicated fans, are indeed complete. And I actually, so yeah, speaking of the questions of whether they are projective or not, in general case, we do not know. In which cases do we know projectivity? We know projectivity for the cases when all the points are concentrated on one of the lines. So by the way, if you have only 2 lines, you have n points on one line and 0 points on another line. This is actually another family of polytopes that you guys could have seen in your life. So 2 associahedra of form Wn0 are nothing else but multiplehedra. And the realization of multiplehedra with the fan that I just described over here coincides with forces realization of multiplehedra if you force that to live in a hyperplane. And so in other cases that we know, when there are just 2 points, as many lines as you like, but just 2 points. And then another realization that we have is when there are just 2 lines and as many points as you like on each of them.
But somehow the question is somehow, is this fan that you just described known to be non-projective in some cases, or?
No. We don't know. We don't have any negative results, and we hope that our fans are projective.
Okay.
It's that.
But in those cases that you realize, it's sometimes not this fan; it's a different fan.
No, it's this fan. It's this fan. Okay. So in the families that I've just described, we have a support function for this fan that I have just described. And if Karim would let me log into Zoom and share my screen. Then to conclude my talk with, I would like to show two three-dimensional pictures of two associahedra, which are like very large. For example, W22, it has more than 30 vertices, so that sort of you could see how what shape the objects would have if they are realized with velocity fans. So I'm logging into Zoom. Meeting passcode 6. Right. Oh, Karim, could you mute?
Turn off, yeah.
Don't know. I have this thing. Am I allowed to share my screen?
Theoretically, yes.
Right. Do you see my screen?
I do.
Good. Then this is just Sage in browser. So this polytope that you see right now, this is W22, which is three-dimensional. And it looks a bit like a spaceship, I think. Oh, sorry for not showing.
No, they see it.
They see it. Good. So what can I say about it as a polytope? You, for example, can see that this is not simple. It has vertices that have valency 4. And it has over here, you can see a little face that has all its vertices 4-valent. So it's not something that you sort of can get as a coincidence, because there is no freedom to move this face in like any direction. It can only be where it is, because it's like very, very rigid. And that's how it looks. And this is W31. It is less symmetric because the lines are different. And again, there are some non-simple vertices. For example, this one. So it's a bit less pretty, but also nice.
And when the polytope is symmetric?
Sorry?
In which cases the polytope is symmetric?
Well, when the arrangement of lines and points is symmetric, like W22 is a symmetric arrangement of lines and points. There are, so the polytope is symmetric, and W31 is not symmetric, so the polytope is not symmetric. I guess W111 should also result in some very good looking polytope. It's also three-dimensional, but for W111, we currently do not have results that says that our fan is projective. I mean, you can brutally sort of Sage check that the fan, Macaulay check that the fan is projective, but we don't know the support function. Okay, so.
But so maybe you want to first realize the two Combinatorics and then try to look at like the boundaries of the amplitude, right? And then look for your associahedron. Maybe this is simpler.
I don't think it will be simple. I mean, first of all, you'll have to define the two permutahedron, because NA does not have a definition of that object, but I mean, what we can do is that we actually, in addition to this fan, which is non-simplicial, because I did show you that there is quite a bunch of 4-valent vertices in those polytopes, but we have a smooth triangulation of this fan. And for the smooth triangulation, you can just describe the wall crossing conditions, and a support function is something that satisfies the wall crossing conditions. And we can uniformly describe all the wall crossing conditions for this smooth triangulation. And then in some cases, we were able to just like describe a point inside the ample cone. Well, because like solving a system of finitely many inequalities is easier than just like finding a support function for a general fan. So our approach to looking for support function deals with the smooth triangulation of this fan. And I mean, I hope we will get it. But currently, proving projectivity of those fans is work in progress, but the fans are complete, and the polytopes that we have as some special cases are nice. So thank you very much for your attention, for being here physically and virtually. And if you have any more questions, I'd be happy to answer them.
So there are analogous, at least structures for three categories and so on and so forth, right?
Yes, I mean, in fact, our paper that we are writing is called not 2 associahedra, but an associahedra. And if you want to describe what is an associahedron, then here what I had lines and points on lines. So for 3 associahedra, you will have in R3 an arrangement of planes. Then on each plane, you will have lines, and on each line, you will have points. And so on for 4 associahedra.
They encode n categories, sorry?
They should encode n categories, but I mean, for 2 associahedra, well, I did not say what they form algebraically. I sort of hinted what is the algebraic problem they are supposed to solve, but I didn't say how. And the answer is, well, so usual associahedra, they encode infinity categories because they form an operand. And 2 associahedra, they form something that is called a 2 operand relative to the operand of associahedra. This is a notion by Nate Bottman and his co-author Sachar Carmeli. The notion of a 3 operand relative to a 2 operand relative to a 1 operand, I'm not sure it's written by anyone, but I guess one can generalize the paper by Sachar and Nate to say what n associahedra form. But for n associahedra, it's harder to draw pictures, and I mean, there are not that many things that you expect to be homotopy 3 categories. Like for the homotopy 2 category, there is an example of such thing that is very expected in symplectic geometry, namely all Fukaya categories together. They should form a symplectic homotopy 2 category. And for homotopy 3 categories, just it's not clear why you would you define them, because it's not clear where you find like an object that you would, an example that you would really like to study.
So does it make sense then also to look at a infinity or something like that?
Maybe, I don't know. I don't know what it is.
Okay. Any other questions?
Do you have a formula that counts the number of facets or vertices of these things?
I don't, but Nate might. I don't know. It's a good question, and I'm sorry that I don't know the answer. I should have prepared better when coming to a combinatorics seminar.
Sasha Estelov, you had a question?
Yes, thank you.
Oh, sorry, I have to put the sound on. Yeah.
Yeah, so the usual associahedron is the secondary polytope of a polygon.
Mhm.
So now, what if you take, say, a four-dimensional polytope whose projection to the two-dimensional projective coordinate plane is a polygon with a number of vertices corresponding to the number of lines. And over every vertex of this two-dimensional polygon, you have like a vertical polygon whose number of vertices corresponds to the number of points on this line. And then you take the secondary polytope of this four-dimensional polytope. Would it be somehow related to...
So you are asking whether these two associahedra have a realization as
not necessarily not necessarily realization. What I described, the secondary fan, is it like coarsening or refinement of the fan that you have constructed, maybe?
I think this is not very likely, because I think that the secondary associahedra have this realization as secondary polytopes, but as far as I remember, this is different from the Loday realization. And our realization, it is mimicking Loday realization of two associahedra.
But I mean, just if we look just at the purely combinatorial structure, is it the refinement or coarsening of this combinatorial to associahedron?
I don't know the answer. By the way, do you know if multiplohedron has a realization as a secondary polytope or is related to any secondary polytope?
I don't know.
Okay, because I'll probably ask you after the talk again what is exactly the construction with which I should be comparing to associahedra, because I'll probably write you a message after the talk, because I'll need to think about it. But no, I don't know about any connections of two associahedra to any secondary polytopes.
Nice. Thank you. Okay.
Thank you.
Okay, thank you very much. Let's all thank the speaker. And then we meet next week again. And I don't actually, Alina knows who's speaking next week, she can say it.
Nick early.
Speak early.
So
But it will start on time, so.
yes, thank you, Kai.
Very good one. Okay, bye. See you.
Thank you. Bye, everyone. Thanks for coming.
I want to ask a simple question.
Oh.
Is it true that double ij equal is somehow symmetric to double ji?
Yeah, of course. They are the same polytope. And the fans are actually isomorphic, but the isomorphism is non-trivial. It is, some invertible map of the vector spaces in which the fan lives, but not the identity map.